Hello, my chemistry students. Awesome to see you today. Well, not see you, I guess. I mean, I can point at you, but I can't really see you. Although maybe some of you believe that I can see you, and then I'm watching you. So unfortunately today I won't be in class, so I made this video to help us kind of move forward. And Miss Hecka's there, so she can help you with some stuff. And yeah, perfect. Let's get going. Oh, before we start, actually, Miss Heck will be our substitute teacher on the days that I'm not here this year. And there's several of them that I've planned already for some conference that I'm going to. So make sure that you're like, you know, being super cool to Miss Heck and that you're sucking up to her, because if you show up on a list of somebody who did not do what they were supposed to be doing or was not cooperative, you can expect that there will be some consequences, as unpleasant as that is. I'm sure that won't be an issue. Let's get rolling. So right now you should have your notes out for ions and ionic bonding. I believe we left off, and I'll back up one slide here. We had left off trying to understand why this thing, the Octet Rule, exists. And we saw here that as sodium loses this outer energy electron, because electronegativity here of chlorine is bigger, it gets pulled by chlorine onto this atom. And that means it loses its entire valence electron energy level. And what's left is the second energy level. And it really pulls these electrons really strongly because they're so much closer to the nucleus now than they way out here. This one way out here wasn't very close. And then once chlorine gains this one electron, it can't gain an extra one, because to do so would be to put the electron way out here in this fourth energy level, and it'd be really a weak hold for it. So basically, chlorine can gain one, but not more than one. And sodium can lose one, but not lose more than one, because now it's holding on so tightly. So we developed that idea last time I saw you. And today we're going to keep talking, and we're going to say that these two things that form, and let me go back 1 second. I apologize for being so chaotic with this. And we'd also said here that because this one lost an electron, it now has a +1 charge. And this whole atom has a -1 charge. Now this +1 and -1, they are attracted to each other just because positives and negatives attract each other. And that attraction between the two of them is what we call an ionic bond. And that's where this next one is. So the opposite charges here of the cation and negative anions. So cations are positive. Remember that cation is positive because there's a T that looks like a plus in it. Cation is positive, anion are attracted to each other, and that creates an ionic bond. Now, Ms. Heck, as we go through this, if you want to pause the video for the kids, feel free. If you guys need it to be paused, feel free. I'm just going to keep rolling. So ionic bonds form when electrons from one atom are transferred to another atom. And we always have two ions that are formed, a positive ion and a negative ion. Now the more electronegative atom gains the electrons, becomes negatively charged, and called an anion. This word anion should cue in your mind a few things. First of all, negatively charged. Next, that it gained electrons. And the reason it did all that is because it's highly electronegative, so it's more electronegative. So those three things from this one word, those three things should be popping in. Now, of course, if one of them gains electrons, the other atom in the reaction had to have lost electrons. And that's the less electronegative atom. It loses electrons. It becomes positively charged, and then we call it a cation. So once again, this word cation should cue up all three of those things. So I'm going to move to the next slide here, so if you need to pause it, please do so. Roman numeral 3, the Octet Rule. The Octet Rule is this great rule that we talked about previously. What it basically says is that all atoms are trying to achieve a full valence energy level, which for all atoms but hydrogen and helium ends up being 8 electrons. That's how it got its name of Octet Rule. Like octopus has 8 valence electrons, what we're trying to get to. Okay. Now atoms can gain, lose, or share electrons to get there. So far we've just talked about atoms with very different electronegativities, so it's all been about transfers and not about sharing. Later on we'll talk about what happens when atoms close to each other on the periodic table, who have similar electronegativities react, we're going to find they actually share electrons. But right now we're going to stay focused on atoms that are metals on the left side of the periodic table with nonmetals on the right side of the periodic table, and those are going to be this ionic transfer of electron thing. So I just mentioned this, but the valence shell for hydrogen and helium, they only need 2 electrons. So for them, a full octet would just be 2 electrons. The rest of them need 8. And remember those 8 electrons, there's 2 in the S sublevel and 6 in the P, and then that's a full valence for each of the other atoms. As an interesting fact, many of you know that the noble gases right here, boom, right there, do not react with other elements. That's why they're called noble, because they act like they're better than everyone else. I'm not going to react with you. That was apparently my nobility voice. And the reason that is because they already have 8 valence electrons, so they don't tend to form bonds. Now that's true of especially the early ones, like helium, neon, argon. But once you start getting to bigger ones like krypton and xenon on down, some of those are more reactive. We can get them to react just because those electrons are so far away. They can be popped off and pulled on a little easier. Okay. That last bit you don't have to know. That's just nice detail. So I'll move on to the next slide. If you need to pause, please do so. So atoms have 2 options when they go to fill up their valence electrons. One of the options is they can gain electrons to get 8 valence electrons, or as we've seen already, they can lose their valence electrons and drop down to the next energy level below, which is already full. That's what sodium did for us. It lost that 1 outside electron, and so it fell back down to that inner energy level, which is already full. But there's 2 options. And let's look at sodium again. Let's look at sodium's 2 possibilities. So there's the electron configuration of sodium, right? So it has 2 electrons in the 1s. It's got 2 in 2s, 2 in 2p, so a total of 8 second energy electrons, and then 1 in 3s. So sodium has these 2 options. It can lose 1 electron, and if it does that, this part kind of goes away, right? And it just has this what's left over, so a full octet. Or it can gain electrons, but to do that, it has to gain a full 7 electrons to pull up and to get a full octet here. So if you can imagine sodium, who is already pretty bad at holding its own electrons, the chance of it gaining 7 more is pretty remote. So this losing 1 electron is how it's going to go. And all atoms, when they have these 2 options, they will always take the one that is the least number of electron change. So whichever one is easiest to do. They're sort of lazy. And I can, I guess, understand that. I can empathize with them. All right, so I'm getting ready to move on. So if you need to pause it, go ahead. All right, comprehension check. So on this comprehension check, I want you to say for each of these elements below, oh, it's coming up all wrong. Oh, that's terrible news. Terrible news. So we'll do this one. We'll just do these together, I guess, each time. So calcium, right? Calcium, if you look on the periodic table, it's in a group 2 element. It has 2 valence electrons. 2 valence electrons. So it has 2 options. It can lose 2 or it can gain 6. I'll let you try to guess what it's going to do. And the option is this one that actually happens. So you do sulfur now. Sulfur is directly under oxygen on the periodic table. So sulfur starts with 6 valence electrons. It has the option of losing 6 or gaining 2. And if you said gaining 2 is the option, woo, winner, chicken dinner. You don't get a chicken dinner. That's not true. So the next one is boron, and our good friend boron is just to the left of carbon on the periodic table. And it has 3 valence electrons. So 3 valence electrons. It has an option to lose 3 or 2, gain 5. And if you said lose 3, you are fantastic. Oh, this is all out of order. This is all out of whack. I don't know what happened. I'm going to skip those guys. All right, last thing we're going to do on this lecture. I know this is kind of brutal. It's not a really great way of doing it, but we got to learn how to do Lewis dot structures. So here's what they are. So a Lewis dot structure shows only, so instead of drawing the entire atom with all of its shells and energy levels, it only shows the valence electrons. So it makes our life a lot easier instead of drawing all this craziness. So let's look how to do this. And the reason we focus on those valence electrons is because they're the ones used in bonding. So it really helps us understand how they're going to bond together. So some steps for drawing Lewis dot structure. So first we write the symbol of the element. So for example, we're going to do a Lewis dot structure for phosphorus. We would write a big P here. And then the next step is to determine the number of valence electrons. So when I look up phosphorus on the periodic table, it's right below nitrogen, and it's in group 5 of the periodic table. So it has 5 valence electrons. Awesome. So the next step is place the 5 electrons, however many it has, in this case 5, around the element, 1 electron on each side, and then pair up if necessary. So there are 4 sides to this letter. There's this left side, bottom, sorry, that's right for all of us. Right side, bottom, left side, top. So what we do is we put an electron here, and we represent electrons with dots. So I put a dot here. Now electrons are all negative, so they tend to repel each other. So the next electron won't actually pair up yet. It's going to go here. So that's 2. That's 3. I've used 3 of my 5 valence electrons. That's 4. And then they're going to pair up and form 5. Now what this tells me is anywhere where there is an unpaired electron, there's the potential of forming a bond there. So phosphorus has 3 bonding sites, and this one that's paired up already, it's not a very good bonding site. Now some bonds can form here, but it's not a very active bonding site. So here 1, 2, 3 possible bonds. Okay. You can see now I'm just going to, let me erase these guys so you guys can see the other ones come on real quick. So here they would come on 1, 2, 3, 4, and then pair up 5, just like we had it drawn before. So these unpaired electrons represent the bonding sites. So try some yourself. Oh man, that came up so badly. I'm not going to re-record this. Oh well. You're gonna have to live with the fact that these all popped up. Is there any way I can get rid of them quickly? I don't know. Is that? I mean, you can totally see what I've done. I don't think that's gonna help. All right. So you'll get some practice today as you do electron configurations in the next activity. But these are what they would look like, right? So 8, hydrogen is 1 here, magnesium 2, oxygen has 6, so it's 1, 2, 3, 4, 5, 6. Pairs up that way. Fluorine, for example, is in group 7, so it has 7 valence electrons. So it would go 1, 2, 3, 4, pair up 5, pair up 6, pair up 7. Argon is paired all the way around. It has no open bonding sites. So I mean, you get the general idea here, hopefully, without having to do it yourself. This activity looks like this. It comes with a little packet, and inside here there are little fleece circles. It would be awesome if you guys did not pick these apart and ruin them today. And Miss Heck, if you want to at this point, there's a handout called Fleece Atoms. If you can make sure everybody gets that, maybe pause the video. So each one of you will get one of these bags of atoms, and what you do is first just take stuff out, and you can see there are these little tiny electrons that come with it. And then there's these atoms, and the electrons can actually sit on the fleece atoms, and you can actually make the Lewis dot structure. So for example, potassium is a group 1 element, so its Lewis dot structure would just be, bam, 1 electron on there. So that would be a potassium Lewis dot structure. So when you're doing this, you're going to actually show these transfer of electrons from one to the other, and you're going to keep going until they fill up. I'm going to let you kind of figure it out from there and see what happens. So the idea is that potassium, for example, it wants to get rid of all of its electrons, bam, it'll be satisfied now. When you get these, on the outside of the bag, you'll notice that there's a little sticker that tells you how many of stuff you should have. Make sure it has that stuff. If it doesn't, let Miss Heck know, and she'll make a note for me so I know that I need to get some stuff replaced. All right, my friends, that does it for our thing today. Enjoy the fleece atoms. We'll practice today, and then we'll work on them some more tomorrow and really get good at this idea of transfer of electrons.